Most of the materials we encounter in everyday life are formed as countless atoms bond together. We're always curious about how those atoms bond and how they arrange themselves within a material, but in reality, this is something we usually picture only in our imagination. That's because this world is simply too small for us to see. Yet a microscope that allows us to directly observe this atom-filled world does exist. While ordinary microscopes rely on light, the microscope that reveals the world of atoms is a special instrument that uses electrons instead. So how does this microscope actually allow us to observe the world of atoms? And what does a world filled with atoms really look like? Is the graphite made of carbon truly arranged in a honeycomb structure? If you stay until the end of this video, you'll see how electron microscopes make it possible to observe atoms and what a world filled with atoms actually looks like. So be sure to press the subscribe button in the lower right corner and let's get started. When we think of a microscope, we probably picture something like what you see on the screen right now. The microscopes we are familiar with use light waves to observe objects, which is why they are called optical microscopes. And if we use electrons instead of light, we get an electron microscope. An optical microscope works by using multiple glass lenses to bend light and gradually magnify the image of an object so that it becomes visible to our eyes. So then, just how much magnification would we actually need to observe a world filled with atoms? Among the elements in the periodic table, the largest known atom, francium, is theoretically estimated to be about 0.5 nanometer in size. Even for an atom that large, its size is so incredibly small that several million atoms could be lined up within a single millimeter. That means to observe a world made of atoms, a microscope would need to magnify millions of times. Yet no matter how precisely an optical microscope is built, its maximum useful magnification is difficult to push beyond about 1,000 times. And this limit is not simply a matter of technology. It's a fundamental limit set by the basic principles of how optical microscopes work. That's why atoms cannot be observed with an optical microscope. To understand why, let's first take a moment to look at a key idea, the concept of focus. Now let's look at a simple example. Imagine two very small circles that appear to be touching each other. As we gradually magnify this object, we begin to see that what first looked like a single shape is actually made of two separate circles. With further magnification, the distance between the two becomes clearer and easier to distinguish. This is what we call resolution. That is why a microscope with higher resolution can produce clearer images even at high magnification. On the other hand, if the resolution is low, increasing the magnification alone does not help. Objects that are very close together will still appear as a single blurred shape. In other words, in microscopy, simply increasing magnification is not the key. What truly matters is how small a distance the microscope can distinguish, that is, how high its resolution can be. However, resolution is fundamentally limited by the wavelength of the source used by the microscope. Here, wavelength refers to the distance over which a wave repeats itself in space. In general, the shorter the wavelength of the source, the higher the resolution a microscope can achieve. Now, the wavelength of visible light, in other words, light itself, is already fixed at roughly 400 to 700 nanometer. Because of this limitation, no matter how precisely an optical microscope is made, its resolution is limited to about 200 nanometer. It is possible to increase the magnification even further, but because of this limit in resolution, the highest magnification that can still provide meaningful information is limited to around 1,000 times. At that level, both the magnification and the resolution are far from sufficient to observe a world filled with atoms. So, what kind of wavelength would we need to observe atoms? To put it as simply as possible, the wavelength of the source must be equal to or smaller than the diameter of an atom. If the wavelength is too long, information from multiple atoms becomes mixed within a single wavelength, making them impossible to tell apart. As a result, we need an observational method with a wavelength shorter than 1 nanometer, smaller than the diameter of an atom. But finding waves with wavelengths that short was by no means easy. And to break through this limitation, one genius physicist created a microscope that used electrons as a new source. At first glance, choosing electrons may not seem particularly special, but in reality, electrons are not something that can normally be used as a source for a microscope. A microscope magnifies an object because light passing through glass lenses is refracted, allowing the light coming from the object to reach our eyes in an expanded form. Light can be bent by lenses and form images because light behaves as a wave. But here's the problem. Electrons are particles with a measurable physical presence. They have mass. They are fundamentally different from light, which can be described as a flow of energy. Electrons cannot be refracted by glass lenses, nor can they be focused to form an image of an object. It's like trying to understand the shape of a baseball bat by hitting it with a baseball. No matter how carefully you swing, a bouncing baseball cannot magnify the shape of the bat. So then, how was it possible to build a microscope using electrons, which are particles? Behind this choice lies a remarkable physical principle that blurs the boundary between waves and particles. Have you ever heard of the concept known as wave-particle duality in quantum mechanics? In simple terms, it means that everything in nature can behave like a particle in some situations and like a wave in others. For example, a baseball is a clearly defined particle that we can see with our eyes and touch with our hands. Yet in theory, it also possesses wave-like properties similar to sound. Those wave properties, however, are so extremely small that we perceive it only as a particle. The electron microscope was created by focusing on this very wave-particle duality of matter. So how could electrons, which have such a clearly defined particle nature, come to exhibit wave-like properties as well? Surprisingly, when electrons are accelerated to very high speeds, they begin to reveal wave characteristics alongside their particle nature. And at that very moment, electrons can take on the same role as light in a microscope. In other words, they behave as waves and can be used as a source. Using these principles, the ultimate instrument that allows us to directly observe the world of atoms is the transmission electron microscope. Because a transmission electron microscope is such a remarkable instrument, one that makes it possible to observe the atomic world, its size and structure are equally impressive. It consists of a section that generates electrons, a section that accelerates those electrons to extremely high speeds, and lenses that guide the direction of the electrons. Now here is one important point. Even though accelerated electrons acquire wave-like properties, they are still particles. For this reason, the glass lenses used in optical microscopes cannot be used in the same way. Instead, by taking advantage of the fact that electrons have electrical properties, electromagnetic lenses are used to control the direction of electron motion using magnetic fields. In a transmission electron microscope, electrons are typically accelerated using a voltage of about 200 kilovolts. At this point, the electrons reach extremely high speeds, approaching about 70% of the speed of light. When viewed from a wave perspective, electrons accelerated in this way have their wavelength shortened to around 0.0025 nanometer. By using such extremely short wavelengths, modern transmission electron microscopes can achieve magnifications of up to several million times, along with very high resolution below 0.1 nanometer. At this level, the resolution is comparable to the diameter of hydrogen or helium atoms on the periodic table. Another important feature of this microscope is that electrons accelerated to about 70% of the speed of light carry very high energy, allowing them to pass through the material being observed. As they do, the electrons emerge carrying information from inside the material as well. You can think of this in a way similar to X-ray imaging used in hospitals. That's why this instrument is called a transmission electron microscope, with the word transmission placed before electron microscope. So now, let's take a look at how atoms are actually arranged inside real materials using this electron microscope. The first material we'll examine is graphite. Graphite is commonly described as a material in which carbon atoms form a hexagonal honeycomb structure arranged in layers. But is this description actually accurate? So now let's observe the world of carbon atoms that make up graphite using a transmission electron microscope. How does it look? On the screen, you can see honeycomb-like structures packed closely together. Now let's zoom in a bit further and take a closer look at this honeycomb pattern. Do you see the small round shapes at each corner of the structure? Those round shapes are carbon atoms. Using this image, it's even possible to measure the diameter of a carbon atom. In this way, carbon atoms bond with neighboring carbon atoms to form a honeycomb structure, and this structure connects continuously to make up the material we call graphite. If we were to magnify an ordinary pencil or a piece of mechanical pencil lead by several million times, isn't it fascinating to realize that it's made entirely of these bonded carbon atoms? So now, let's take a look at another material. This time, the material we'll examine is gold. Gold, which we are familiar with as a gemstone, is of course also a material made from atoms arranged in a regular pattern. So how does gold differ from graphite? If we look at an image taken with a transmission electron microscope, we can see an atomic arrangement that is quite different from the honeycomb structure we observed in graphite earlier. Let's zoom in a little closer. Just like carbon, all of the round shapes you see on the screen are gold atoms. In terms of shape, they're not very different from carbon atoms. The difference lies in how they are arranged. Unlike graphite, which has a two-dimensional planar structure, gold is a metal with a regularly ordered three-dimensional lattice. In fact, the basic structure of gold is built around a cube, with gold atoms positioned at each corner and at the center of each face. Now, if you look at this structure straight on, what do you notice? It matches exactly what we observed with the electron microscope. In this way, gold is formed by atoms that hold their positions and pack together densely to fill the material. And by analyzing materials at the atomic level using this electron microscope, it becomes possible to predict what properties a material will have. For this reason, transmission electron microscopes have become an essential tool in the fields of material science and related research area. However, they also have clear limitations. The instruments are extremely expensive, often costing tens of millions of dollars, and in some cases even more. In addition, stable operation requires highly trained specialists, typically at the graduate level or above. As a result, while transmission electron microscopy is a very powerful analytical tool, it's not something that can be easily accessed or used by the general public. There is an interesting story from the history of science connected to this microscope. The transmission electron microscope was first developed in the early 1930s by the German physicist Ernst Ruska. When this technology made it possible to directly observe structures at the atomic scale, some physicists at the time believed that science might soon reach its limits. After all, if we could now see the arrangement of atoms inside matter with our own eyes, it seemed as though there might not be much left to discover. Being able to observe atoms, something that had existed only in imagination until then, was an enormous shock. But as time passed, the reality turned out to be quite the opposite. The more closely scientists examined the inside of matter, the more unexpected phenomena appeared, along with questions that were even harder to answer. Rather than marking the end of research, the transmission electron microscope opened the door to an entirely new era of scientific exploration. In recognition of this achievement, Ernst Ruska was awarded the Nobel Prize in Physics in 1986, and today, the transmission electron microscope has become an essential instrument in the field of material science research. Today, we explored how scientists found a way to observe the world of atoms, a world far beyond what our eyes can see. By going beyond the limits of light and using the wave nature of electrons, the transmission electron microscope opened a window into the inside of matter, allowing us to examine atomic arrangements and bonding structures directly. This technology became much more than a microscope for seeing smaller things. It turned into a powerful tool for understanding and predicting the properties of materials. When we look back at the original idea behind this instrument, it's hard not to admire the insight of the scientists who transformed what once seemed impossible into reality. That brings us to the end of today's story. I'll be back next time with an even more fascinating topic. You've been watching Dr. Sai Vera Studio.